You know that digital computer consists of three very important resources. For example, if you see, it consists of central processing unit, that is the first element, and then it consists of memory, which is the second one, and the third one is the input-output devices. Now the question comes is that if you have these three elements, which is the memory, input-output devices, and the CPU, how do you connect them and how do you communicate with these three elements? Because a program, you know, is a collection of instructions, and that instructions normally reside in the primary memory and which has to be executed by the CPU in order to give a result. So there should be two-way communication between the memory and the CPU, as well as between the input-output devices and the CPU. And also, in some cases, there could be a direct communication between the input-output devices and the memory through a special mechanism, which I will explain you. Now, if we explain these three elements, you see that these three elements are connected by a set of conductors, which is normally called bus. And the bus is basically a communication link between these three elements, that is the central processing unit, memory, input-output devices. Now, if we go, give you the block diagram of a digital computer, let us see what happens. Now, you see that central processing unit, the memory, and the input-output devices are connected through set of conductors, which is which is called the bus. Now, in order to see that this is the central processing unit, which is communicating with the memory, input-output devices, which is called the peripheral, and this is the interface unit or interface hardware, which communicates with the CPU and the memory. Now, if you see that this memory and input-output devices are connected to the CPU through three independent buses. One is called the data bus, another is called the address bus, and the third one is the control bus. Now, you appreciate that address bus is required because one has to give the unique address to the memory in order to access a particular data or parameter. And the address bus, as discussed, is normally an unidirectional bus. And the data bus, because you have CPU has to read as well as CPU has to write, so it has to be bidirectional. Now, the control lines are basically to decide whether the data is for the memory or it is for the input-output devices. So, because it is a single bus computer, there must be a different method to differentiate, or different control signals should be available, which will tell you that how to when to know the memory and how to connect the peripheral devices. Now, if we go to the next one, you know that what happens is that when you have memory and the input-output device, they are connected to the CPU. There is something called the memory space, and another is called the I/O space. Now, in a single bus computer, what happens is that there must be some address line is shared by the memory as well as input-output devices. So it has to be differentiated by certain control signals, which will say whether it is for the I/O or whether it is for the memory. Now, if you have seen that I have made a box here which is called the interface, and interface was having certain amount of registers. Now, if you see that there are some registers are basically for the buffering data to and from the CPU, and some are for holding the status information about the device and the interface so that it can be examined by the CPU, and some are for retaining the commands. So basically, one can say the interface is a hardware which consists of certain registers for data buffer, for input as well as an output, for command register, which will hold the command which is generated by the CPU to decide whether it has to do reading or writing, and then some of the status information, because the status information is very important, because some of the peripherals are normally slower than the device, as a result of which there must be a status information to say whether the peripheral is ready or not. Now, if you see that type of transfer or the communication that can be done by the CPU with input-output devices. You know, there are three ways one can do. One is called the programmed I/O, which I will explain you later, and then there is called interrupt. Of course, today's discussion is mostly on interrupt I/O, and then there is something called the block transfers. Now the question comes, what is a programmed I/O? The very fact that the programmed word is there means a programmer should be able to access the input-output devices with a set of instruction, which is an input instruction or an output instruction. So basically, it's a transfer of data, which is it could be single byte between the CPU and the I/O device with the help of an input-output instruction. Next comes the block transfer. Now, first statement what I made, that normally the peripherals are slower than the input-output devices, than the CPU, sorry. So in this case, what happens is that one has to go for a programmed I/O. There is another case of transfer where, you know, you want to transfer a block of data, which is a sequence of bytes between the memory and the high-speed device. In this case, the high-speed device can be for example, a disk or any other fast device. And this access is called direct memory access. So that means a block transfer is nothing but a transfer of a packet of data or a sequence of bytes between the memory and the high-speed input-output devices. Now, so far as programmed I/O is concerned, this now so far as the programmed I/O is concerned, it is the simplest of all I/Os. And now let us first see what is involved in the programmed I/O. Now the first thing what is required is, since the peripherals are slower than the CPU, so there must be a handshaking signal between the CPU and the input-output device. So that means if you see, first is that one has to check whether the data input register is ready or not. If it is not ready, it has to wait till the device is ready. This is called the handshaking, or reading the status information or the ready bit of the peripheral devices. Then you have to input a byte. In this case, of course, a byte. In some of the machine you can handle word, and then you can operate on the byte if you wish, and after that you have to keep on looping. So that means what it comes from this is that since CPU is faster, and in fact it is much faster than any other input-output device, the CPU instruction can be executed at a faster rate than the device can give the data or take the data. So CPU has to wait, or CPU has to poll the device such whether it is ready or not. So the implication is that in this mode of thing, what happens is that now if you see that programmed I/O is conceptually very simple, because you have a set of input or output instruction. With the use of input and output instruction, you can communicate data or transfer the data between the peripheral and the input-output and the CPU. So now what happens is that when you do this, the CPU is not doing any useful or meaningful job, because CPU is trying to accept or it is waiting for the ready bit to be on. So what it implies is that if you use this programmed I/O, CPU, which is mainly for number crunching or it is mainly for the computation, it is not doing that. It is totally blocked in the input-output communication. So this is not an elegant way, and especially in a computer system where you have to have a lot of activity going on. So the I/O, programmed I/O, is not a right choice to do this. Now comes that if you don't have a programmed I/O, then what is the alternative you have? Now if you see that there is some other method which is called the interrupt. Interrupt, as you know, is a asynchronous event or a sequence which allows you to communicate, or it will communicate between the input-output device and the peripherals. Now, if you see, if you take an example, before we talk about the interrupt, let us say that we are taking a case where you have that is, suppose I have a input-output, a keyboard connected to a computer, and now somebody is trying to press a key. And if you, let us assume that I have the speed, a person can have 10 characters per second. That is the fastest speed he can do, which means is that he can put one character in 10 milliseconds. Now, if I assume, or if I say that computer can accept a data at the rate of 10 microseconds, then what it implies is that 99.9% of the time is wasted in by the CPU in checking whether the input-output devices are ready or not. So this is not a correct solution. So the next alternative is to avoid certain, this sort of a polling by which the CPU is kept continuously busy. And instead of that, let us talk about an interrupt sequence. An interrupt sequence is an asynchronous event that prompts that prompts the CPU to initiate a fixed sequence of operation or a fixed sequence of a program, which is known as the interrupt sequence. And the program or the routine that is executed in response to the interrupt is called the interrupt service routine. So now, to give you an example of an interrupt, let us say that we have a telephone, and if when you are reading a book, and if the telephone rings, what you can do is you can put a you can put a tag on a page in which you are reading, and you can lift the telephone. Now, suppose the telephone, if you have a telephone which doesn't ring but it blinks a light, then what happens is that you cannot do reading simultaneously waiting for a call. So at that time, what will happen is that you have to be always looking at that light whether it blinks or not. So the interrupt is also like that. In interrupt, what happens is that CPU can do a sequence of operation without bothering whether any input-output device is asking for a data. But when input-output device is trying to get the data or take the data or transfer the data, it causes an interrupt to the CPU. Now, what it means is that the CPU stops the current, finishes the current instruction, and then it goes to the interrupt service routine, which is a sequence of program or sequence of instruction which has been written by a programmer to service that input-output device. So the advantage is that CPU can continue its normal process of computation, and input-output device can cause an interrupt to the CPU. So, but what is the meaning of it? Meaning is that CPU should have a signal which is called the interrupt signal, and that will allow the CPU to know that somebody is, some input-output device is trying to cause an interrupt. Now, it is like, when the telephone rings, so similarly, you should have an input signal or a pin which will say that the interrupt is coming from the external device. Now, so one can say that the interrupt is nothing but a subroutine, or it is a procedure. Now, you know what a subroutine is? Subroutine is basically a set of instructions which is written in the part of the memory, and whenever you give a call to a particular point, then it goes to a subroutine. That means, but in an interrupt, first I said it is an asynchronous event. The very fact it is asynchronous means you don't know at what point it will come. And the very fact you don't know at what point you come, you cannot put a program at a fixed look. You cannot put inside your program. It should be in some common place, so that when an interrupt comes, you should be able to pass on the control to the interrupt service routine. So only the difference between the interrupt and the subroutine is, interrupt is an asynchronous process, subroutine is synchronous process, because you know when to go and what to, but in interrupt you don't know when an input-output device will will ask for an attention. Now, with this interrupt, and so now we have seen that interrupt is a very essential part of any input-output device. Now, before I go to the interrupt mechanism, let us say that what is a standard input-output instruction. Now, if you see, the input-output instruction is also, you have an instruction called in, and you have a port address, Similarly, you have an instruction which is called out, which is the port address. Now, the port address, as discussed in the earlier discussion, that you can have 0 to 255, which means that you can have connect 255, 0 to 255 means 256 input-output devices. Now, very fact you have to, because you have a separate read line and write line, so you should be able to access 255 input-output devices. Now, with this input-output instructions, now let us see what an interrupt can do. As I told you, the interrupt is an asynchronous process. The very fact it is an asynchronous means it has to come either from an external device or it has to come from an internal device. Now, if it is an internal, it is called software interrupt, and if it is an external, it is called it is caused by the external input-output devices. Now, software interrupt is very essential because sometimes what may happen is that when you may be interested in finding out or in debugging a program, you may be interested in putting a breakpoint or a control such that when a particular instruction is executed, you want certain message to come. So in this process, a software interrupt can be used. I will explain you the software interrupt, which is an internal interrupt. But the point here is interrupt can be internal or it can be external. And if it is an external, it has to come from the external devices. So there must be certain hardware pin available on the CPU through which you can cause an interrupt. Again, if it is an external, it can be non-maskable or it can be maskable. But the very fact that the word non-maskable means it has the highest priority. Now, in 8085, that trap is the highest non-maskable interrupt, and the question now comes, why do you need non-maskable interrupt? Now, that in a non-maskable interrupt, what happens is, suppose if you are designing a computer and if the power fail or that sort of a restart you have to use, then you can use this interrupt because it has the highest priority. Maskable interrupt is where CPU, it is not that your interrupt will be always acknowledged, but it will be only if it is mask is enabled, then only the interrupt is acknowledged. It is something like this, that suppose you have a telephone which is in the next room. If the ring comes and if it is a concerned person is talking, then somebody can call you. So maskable interrupt is a case where if the interrupt is enabled, then only the interrupt pin which are connected to the CPU will be acknowledged. Otherwise, even if input-output devices causes an interrupt, nothing is going to happen. So in external interrupt, if you have multiple interrupts, there must be certain amount of priorities. The priorities in the sense is that if, for example, I told you that non-maskable interrupt is the highest priority, and the maskable interrupt again will have different priorities. Now, if we see the different interrupts which are allowed in 8085, the first is the trap, and the second is called the RST 7.5, which is basically, it is called restart. RST is an abbreviation of a word called restart, and 7.5, then it is 6.5, and then it is 5.5, and this is INTR, which is for the external device. Now the question comes that why they have provided, the manufacturer has provided three such interrupts called RST 6.5, 5.5, and 7.5, besides INTR, which is also an external interrupt. The point here is that I told you that RST 7.5 and 6.5 has certain priorities. So if you have, and if you see, the interrupt has the lowest priority, INTR, and the first one is the trap, which has the highest priority, then comes 7.5, which is the second level of priority, and third is 6.5, and the fourth is 5.5. Now comes the triggering level, because since RST is an external signal, one has to define whether it is a level sensitive, or it's an age sensitive, or it's a combination of level and age both. Now, but if you see, the trap, as I told you, is level A and age sensitive. What it means is that in order the trap pin to be active, the signal has to go from low to high and remain there. So that means trap is a level as well as age sensitive. Similarly, RST 7.5 is a positive age sensitive, and in 6.5 and 5.5 is a level sensitive. That means if it goes high, then only the interrupt will be, if interrupt is enabled, RST 6.5 and 5.5 will be energized. And in case of, when I say trap NMI means non-maskable interrupt, and RST 7.5 is a maskable interrupt, and all others are maskable interrupt. So now we see that 8085A has got 5 interrupts, 5 external interrupts. The first one is a trap, which is a non-maskable interrupt, and the remaining 4 are maskable interrupts, which out of which 3 are reset 7.5, 6.5, and 5.5, and the fourth one, which is an INTR. Here I have written a thing called call locations. Now what does it mean? As I told you, that a trap, any interrupt is an asynchronous event. And the very fact is that it is an asynchronous event, I cannot write inside my program. It should be kept in a common place. Because whenever a trap is encountered by the CPU, if the current instruction will be completed, and then the control will go to a location which is corresponding to 0024. H means hexadecimal address in the memory location. So the condition is that you should have a program at the location 0024. Similarly, for RST 7.5, you have another vector which is a location 003C. So that means these are called vector address, or these are the unique address. Whenever a trap comes, it has to go to that unique location. So it is the responsibility of a programmer to define a set of instructions in that particular location. And if the programs are not kept in that location, then the trap will not be, though it is acknowledged, but the trap will not do the job what you expect it to do. Then the last one is INTR, where I have said variable. And here there is a certain catch in it. If I say variable means, what does it indicate? That whenever an interrupt, first I said interrupt is external. So if it is an external, one has to provide a certain address. In case of a trap, RST, the addresses are well defined. So it is a hardware vectored address. Whereas in case of an INTR, it is a software vector address. That means it is the responsibility of the input-output devices to supply the vector address through the data bus. And now the question comes, how do the interrupting device know when to supply the address which is a unique address? Now in this case, what happens is that in response to interrupt request, the CPU, if a mask is not, if interrupt is enabled, then it will provide a signal called interrupt acknowledge, which I will show you in a block diagram. In response to the interrupt acknowledge, it is the responsibility of the input-output device, that is the interface which is communicating that, to provide a call instruction such that it goes to a unique location where your program is there. That means now if you see, the interrupt has an overhead in terms of supplying the software vector, whereas trap and RSTs do not have software overhead because the interrupts are well defined. So certain specific applications which are well defined, one can use trap and RSTs. And interrupt request is a thing where it can be connected to a set of different peripherals where the vector address can be provided by different interrupting device. Now comes the software interrupt, which is basically called restart or RSTs. Now, if you see, the software instruction comes like this. It is called RST 0, 1, and it goes up to RST 7. Now, there is a code for it, and the hexadecimal code is, for example, C7, CF, and the locations. Whenever there is an RST 0, it goes to the location 000 in the memory. It goes to the location 008 whenever there is an RST 1. Now you see the difference here, that always there is an offset of 8, and these addresses are hexadecimal. So that means between RST 0 and RST 1, there is an offset of 8 memory locations. Now with this so these RST instructions one can use for software interrupt, which is for debugging purpose, or it can be for writing certain other specific programs. Now if I explain the total block diagram of the interrupt mechanism, which is normally supported by 8085, you see that I have a flip-flop which is basically called interrupt enable flip-flop, and this is the interrupt enable flip-flop which gets set when you execute an interrupt enable instruction, and then it gets resetted when you disable the interrupt or when any interrupt is acknowledged. Now, if you see that so far as the interrupt is concerned, it has to provide the vector addresses as mentioned here, and this set of AND gates, what you see, is basically enabled by interrupt enable flip-flop. That means if this is on, then only the corresponding flip-flops which is there, they will be energized. And then we have another this whatever I see show here in the mask, these are the mask registers which are inside the CPU and which are can be set or reset by using special instructions called set interrupt mask, or it can be reset. It can be read by RIM, which is called read interrupt mask. Now this RST flip-flop, RST is an H. Here you can see that there is a flip-flop here which latches the thing, and corresponding to this RST or 6.5, and this there is no flip-flop because it is level sensitive, and the trap, it goes directly inside the CPU. It doesn't enabled by the interrupt enable flip-flop because it is non-maskable. So for an interrupt, what happens? What is the first requirement? You have to energize the corresponding bits of masking. If you want to energize this one, plus you have to enable the flip-flop in order to by executing an interrupt enable flip-flop, and then the corresponding interrupt will be responded, and once you respond that particular instruction, it will go to this unique vector locations or vector addresses. Now if I summarize the steps of what happens when an interrupt comes from an external line, which is INTR, which is called maskable interrupt. Now the first step is you have to enable the interrupt by an enable interrupt instruction, and then you have to when the microprocessor is executing any instruction, it checks all the 5 interrupt lines, and then depending upon that, you have to it has to execute once the interrupt line goes low, the interrupt line is high, then interrupt is an interrupt is enabled through the instruction EI, then the corresponding interrupt will be acknowledged, and an interrupt acknowledged signal will be generated. And if the interrupt acknowledged signal is generated, it is the responsibility of the external hardware to provide or to insert an RST instruction on the data bus, and then as the CPU will go to that particular program counter will be initialized to that code, and the interrupt service routine will be executed. And this is, so that means interrupt is basically an asynchronous process. With the help of interrupt, one can connect any input-output devices, and it saves a lot of CPU time, because CPU doesn't have to really bother for whether any input-output devices are trying to cause an interrupt or not. And with the help of interrupt, the CPU can do its normal job, and whenever any input-output device is trying to cause an interrupt, it has to be applied through some hardware pin, or which is the hardware signal of the interrupt. So if somebody wants to connect any devices, for example, any peripheral devices, interrupt is the best method of an asynchronous transmission. For the slow devices, for the fast device, of course, one can use direct memory access or the block transfer. Of course, that has not been discussed here, but that is another way of because that allows you to transmit the data from the memory to the input-output device without the intervention of the CPU. That is the fastest method, and interrupt is the most elegant. Of course, one has to take care of enabling the interrupt in case of a maskable interrupt. One has to put certain interrupt service routines at the time at the proper place, otherwise interrupt will not be executed. And one last point here is, whenever interrupt is acknowledged, interrupt enable flip-flop is cleared. So the next interrupt, in order to initiate enable interrupt instruction, has to be executed. And this is all about what I'm supposed to say about the interrupt thing.